All right, so sorry, physicists. I am doing this with my phone right now because my iPad is acting more like a P-pad. Um, so here you'll get the chance to see these wonderful videos that the other physicists did down at the pavilion. But what we have here is a hand that has been in a terrible shop accident, so all four fingers are cut off at the first knuckle, releasing a tennis ball at the top of a ramp. Okay? And so the question that I have for the class right now, and I suppose I'm not left-handed and you're all about to discover that, but because I should have this touching the ground, because it wasn't thrown, it's not a projectile, it's just being released at the top of the ramp. But the question that I have for you, class, is at this moment, once the hand has been released, what are the forces that are acting on this tennis ball? Okay, so gravity, yes, assuming, now, I haven't established that this is happening on planet Earth, but that is a safe assumption. I don't know what. So we have the force of gravity, and, oh man, this is going to be so nauseating. I need to be careful not to whip this thing around. So we have the force of gravity, and what is the direction of the force of gravity? Yes, very good. Okay, so we've got... Wow. This is awesome. Okay.
You are doing it left-handed and behind yourself.
I am.
It's not. That's actually.
Thank you. Yes, admire my talents. So, other physicists, I just want you to know that the idea that this class just had is we should have a class that's just me telling stories of my life, which then the class turns into a feature film. So this is the state that we're at this point of this class, okay?
And also, what's his face? The plane guy.
Oh, yes. Yeah. Yeah. No, I mean, I had 4 marriage proposals before I finally said yes to Mr. Ferris. I mean, there's a lot in there. There's a whole lot. There can be a head plot and a heart plot to this film. For now, however, our subject is this tennis ball, and we need to care about it, the forces acting on it. So, yes, so we have the gravitational force. Okay, and it's basically the center of gravity of the tennis ball, and it is being attracted by the center of gravity of the Earth. Now, technically, yes, the center of the Earth is not right there. That would be terrifying, magma. But, technically, in this diagram, is the Earth the only object that is exerting the force of gravity? What else is exerting the force of gravity? Yes. So the tennis ball is actually also pulling the Earth towards it.
What? Wait, are we pulling the Earth towards us?
Mm-hmm. Here's the thing, if we were suddenly to be teleported, all of us, into deep space, so we were away from any other massive bodies, we would be like skydivers. We could just reach out our hands, and we would all just be drawn to one another, and then we could just be in a hand-holding circle in space. Yes.
I mean, we'd all suffocate, but.
Well, I'm imagining we also, like, as everything else around us disappears, spacesuits appear. That's equally plausible. But so actually, right now, the hand that is exerting the force of gravity on the tennis ball. The tennis ball is exerting the force of gravity on our hand. And this is what I say. If we could manipulate that in the same way we manipulate the electromagnetic field with batteries, like using the force from Star Wars would be totally possible. Because there actually is, there is a force of attraction right now between, my hand and the water bottle. And if I could modulate that in any way, if I could just have a gravity battery that I could apply directionally, and also not just control the direction, but control the distance over which I was applying it, I could totally just suck the water bottle into my hand. Because it already exists. The attraction between matter already exists. Now, technically, we can construct anti-gravity. So we can construct a force in the opposite direction that repels, We've only been able to do that in the laboratory at the atomic scale.
How does that work?
We'll get to that in the fourth quarter. Okay? But technically, in this diagram, the gravity, there's gravity between the hand, the ball, the ramp, the earth, the hand, the earth. It's just like everything wants to just get close. Everything wants to get close. Except for on the atomic level, we also have the strong and weak nuclear forces that are also, and we have the electromagnetic forces, like we have, there's a lot of forces of attraction and repulsion that is happening at the molecular level. So if you're ever feeling that happen in your relationships, it's only normal. That is literally happening to our entire being at all times, at every level. Okay, but the reason why we talk about the force of gravity and we don't draw all the other little arrows that would show all the forces of gravity in this diagram is because the other ones are so small, because the Earth is so big compared to everything else in the picture. And so it just completely overwhelms all the other forces that are in the picture, except for one. So what is it that is preventing this from being a free fall diagram where the ball just falls straight down? The normal force. Sounds pretty basic. It's just like normal. But what is the normal force? How should I draw the normal force in this diagram? Direct. So would it be a vertical line right here straight up?
Well, on a ramp, it's different. It's perpendicular to the slope.
That's right. It's perpendicular to the surface. So that's why if we just rest the ball on the floor, we don't expect it to start going anywhere. Because if the surface is totally flat, in other words, if the surface itself is perpendicular to the force of gravity, then the floor, I mean, this is why we're not being sucked into the magma at the center of the Earth right now, thankfully. It is because the floor is pushing us up to the exact same degree that the center of the Earth is pulling us down. So, thankfully, I mean, isn't it convenient that that's happening all the time? That there's a force provided that is preventing us from being sucked to the center of the Earth. But imagine if we lived on Jupiter. Jupiter is a big giant ball of gas. It would be a terrible place to visit because you would just get sucked to the center and be crushed by the massive atmospheric pressure. So that would be a terrible vacation. Definitely, before you book a vacation to another planet, check to see whether or not it's a gas giant. Because no normal forces will be provided. You will just get sucked straight into the center. Boo. Yeah, I want my money back. But I'm dead. Okay, so I guess I'm just going to have to, I'm doing it this way, so I guess I'm just going to have to keep doing this left-handed. But anyway, there's also this force, the normal force, which is perpendicular to the surface. Okay? So now my question to you is, at this point, how does SOHCAHTOA come in?
Oh, you can find. Well, they're at different, like the forces aren't acting perpendicular to each other, so you have to split them up and find the x and y components.
Yes.
So
So
that you can actually know.
and what's the whole, I mean, and really, on any science experiment on Earth, what is the force that is never going to be removed? It's always going to be present in the experiment. Gravity. So this downward arrow is always going to be here. So whatever the other arrows are, we have to break it up into the components that are in line with this guy and that are out of line with this guy. We always have to break it up. And it's because, you know, at least while we're earthbound, we're never going to get rid of this one. It's always going to be there. And as we've tested with the free fall thing, it's also actually creepily consistent and therefore predictable. Now, I'm glad that it's predictable, but it's weird that it's so consistent because there's so much that is inconsistent. So the whole science around why then with these force diagrams and why we have to break it up into its vertical and horizontal components is for the one simple reason that our laboratory is always going to be saddled with this guy. Until, you know, well, except for now we do have the International Space Station, which technically is not gravity free, but since the entire space station is in free fall, it's like there's no gravity. Which was the first clue as to whether or not gravity itself might be an illusion. It's like, how can you separate? Because we're saying, well, no, actually, because I think, did you guys talk about this in class with the space station, whether or not it's actually zero gravity or not?
Yeah.
A little bit. So here's the thing. Have you guys ever been on an elevator that has suddenly dropped?
Yeah. Wait.
And all of a sudden it feels like you're floating?
Your organs go.
Yeah, exactly. Or like if you're on a roller coaster.
Yeah.
And at the very beginning where it's kind of like, I'm glad the seatbelt is on me because otherwise it feels like I would just be floating here. Like you can actually sort of like feel your derriere. Yeah, exactly. All of a sudden you're pushing against the harness instead of your tushkis pushing against the seat. So that's what's happening with the space station for an extended period of time. You get it far enough up into the atmosphere, it's still falling towards the Earth. But the path is parallel to the Earth, so it just keeps falling around the Earth continuously. So it's like getting on that roller coaster, and then it just never ends. That part at the beginning where you just drop off the steep thing, it just keeps going. And you're wearing no harness. So now you can just float around in there because everything's falling together. It's like being in that falling elevator. You know, imagine if the roller coaster, instead of a seat with a harness, was just like a big cylinder. Once it falls and you're falling, like what's going to hold you to anything? What's going to hold you to the seat? The seat's falling away from you as fast as you're falling towards the ground. So all of a sudden, it seems like there's no gravity anymore. In other words, the normal force is totally removed. Now, we can create that by being far away from any massive bodies. So we can create that just by going out into deep space and being far away from any planets or anything else, which is pretty easy because there's a lot of big empty open space out there. Or we can artificially create it by putting something into orbit. And all satellite orbit is just something that's falling and never hitting the ground because it's too far away. So it's just constantly falling towards the Earth. And that's what the moon is doing to the Earth. The moon is constantly falling towards the Earth and never hitting it. It's sort of like star-crossed lovers. It's so poetic. And I have to believe that these are the things that are influencing our art. Like these are the phenomena that we're witnessing and we're experiencing at some sort of visceral level. And then we have to find a way to express them because there is something that's just so baseline and meaningful about always falling for someone and never touching them. I mean, that is, and that's the moon's relationship to the Earth. That's the Earth's relationship to the sun.
Wow.
Always falling, never reaching, never landing. Nor do I. Yeah, talk about another bummer of a vacation. Move over, Jupiter. Here's Helios. Instant incineration. Yeah. So the point being then, though, is it's kind of like, well, if we can artificially create a gravity-less environment so easily, you know, just by getting a little ways off of the planet, do we actually have any proof that gravity actually, like exists at all? Or is it all totally relative? And is that where the theory of relativity might come from? So we'll find out in the fourth quarter. So anyway, all this to say, to go back to this Newtonian stuff, which is just like basically how things move on Earth. Here's the deal. We've got to break Slanty here into his components, because there's going to be one that's going to be in line with gravity, and there's going to be one that's out of line with gravity. And so that's the whole reason of like where the SOHCAHTOA comes in and why we have to break it up. Okay, I apologize, because to do this part, I really just have to write it with my right hand, and then I will show you the result.